Hi and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about Newton's first law. Newton's first law for forces. This is going to be kind of a continuation of our discussion of forces and Newton's laws. In my previous video I gave a basic overview of Newton's three force laws, and now I'm wanting to go through each of them in turn, as well as some other related topics. In today's video, I'm going to basically be giving a little discussion of Newton's first law, why it is the law of inertia, and what it's basically used for. So you'll recall that Newton's laws are three laws that govern forces and how matter interacts with other matter via forces. So of the force laws, Newton's first law was actually formulated a few hundred years before Newton's time. The original sort of formulation was by a professor at the University of Paris, Jean Buridan, who basically was just trying to describe motion in the cosmos. And he essentially says that planets continue in their orbits essentially by moving through a region of space where there's no friction. So I believe maybe he said something more along the lines of a region of space where there's no retarding force or no resisting force, and so therefore they continue in their motion sort of unimpeded. Now this is a bit of a simplification. We now believe, of course, that there are forces in outer space. If you consider gravitation to be a force, for example, then all of the planets are experiencing a force from gravity. So they aren't experiencing no force. The main point, though, is that objects don't need an applied force to sustain motion, which was a big reversal from, say, Aristotelian motion, in which a force was needed in order to sustain motion. And the breakthrough here is that on Earth, when you, let's say, toss something through the air, you have air resistance, and so the object slows down. If you push an object on the table, you have some air resistance, but you also have friction from the table, and so the object slows down and stops moving. And so you have to kind of like keep pushing the object to keep it moving when you are dealing with these terrestrial applications. But the thought was, well, if we go into outer space, there's no resistive force from like rubbing against a table or sliding along a table, and no air resistance. So you wouldn't need to have any force applied in order to keep the objects moving. And that is essentially an early formulation of Newton's first law. Newton's first law basically could be written in words like this. Objects at rest tend to remain at rest, and objects in motion remain in motion with constant velocity unless acted on by an unbalanced force. That is to say, unless there is some total force acting on the object, some non-zero unbalanced force that's not opposed by a second equal force, then the object is going to be at rest if it's at rest, and the object is going to be moving with a constant velocity if it is already moving. In equation form, we usually simplify this to a simple statement that looks something like this. If the sum of forces acting on an object is zero, then it implies that the velocity will remain constant, which is, if you'd prefer another way of saying acceleration, is zero. So we could say velocity equals constant. And note that an object at rest would have a velocity of zero. So this can be written also as acceleration equals zero if you'd prefer. Either one is a valid way. And actually, in the full Newtonian synthesis, we would have to introduce a new term called momentum, which is not changed, but that's for a totally different video. So this is sometimes called the law of inertia, and the reason being that this tendency to remain at rest, or this tendency to remain in motion with a constant velocity, is sometimes referred to inertia. And we measure inertia with a quantity called mass. That again may be for a different video. So this is Newton's first law in words. This is Newton's first law in equations. Sometimes this phrase unbalanced force is also called net force or total force. So I'm going to put a little box around that and say net force. So if you see the word net force, that's what that means. Or total force, and the force should be external to the object or system. Now this reframing of the relationship between forces and motions essentially means that we can go back and look at these examples, these terrestrial examples that Aristotle and others had looked at when they first formulated this idea that you needed a force to make an object move. Essentially what's going on here is if you have an object that is, let's say, moving along a tabletop or the ground or something like that. So I'm going to draw this as a box moving along the ground. And maybe you have some initial velocity here. Why is it that a force is needed to keep this in motion? Well, the answer is because there are other forces that act on this object. For example, there's already a force from the air resistance. I'm going to call that F air. And there's also a force from friction, F friction, both of which have to be overcome if this object is to have zero acceleration. If these two forces aren't overcome, then I don't have a net force of zero, and therefore this object does not have to have a constant velocity. In fact, we would expect it to slow down. We'll talk more about that in Newton's second law. The point being that we would need an additional force in this direction, which we would call F push or F sustain or something like that, to sustain the motion. But if we were absent the air resistance and the friction, we wouldn't need this pushing force to keep the object moving. Okay, this Newton's first law, the sum of forces equaling zero, basically means that we expect for the air resistance and the friction force, which are to the left, and so we'll call them negative, to be balanced by this pushing force. And so this is a balanced system. So balanced system, and therefore velocity is constant. We also have the other kind of possible case, which is what happens if I have an object that is sitting on a level surface like this and initially v equals 0. And what we want is for this thing to basically start moving. What would be needed? Well, to get it moving, I need to have not zero total force. So to make it stay, I need sum of forces equals 0. So what forces might be acting on this system? Well, we will learn later that gravitation, generally speaking, acts on objects that have some mass. So there is a force from gravity. Therefore, it follows that there must be some other force present in this system in order to prevent the object from falling through the table. That other force, in this case, is called the normal force. And we'll have a whole set of videos about the normal force later, Basically what the normal force does is it's a force that is between two solid objects that prevents them from being able to pass through each other. There's sort of enough space between atoms and between the electrons and the nucleus that for all intents and purposes objects should be able to pass through each other, but you have this normal force that prevents it if they're solid. Again, we'll learn more about the normal force in a different video, including why it's called the normal force. But for now, we just know that there exists a force that prevents the solid block from moving through the solid table that it's sitting on. And so that is the normal force, and in this case it balances gravity. What about friction? Well, as long as I'm not pushing on the object, or anything else is pushing or pulling on the object, friction will be zero. If I start pushing on the object, so small push, it's possible to have a small push such that the object doesn't move. So no moving. How is that possible? Well, we basically get a small amount of friction which resists the motion. So this resists motion. This is what's called static friction. And it turns out that this static friction has a variable value from 0 all the way up to some maximum value. And again, we'll learn about that in a different video. The maximum value is the value which, if I exceed that value, if I push harder than that much, the object starts moving, starts sliding. But if I don't push harder than that, then it's stuck in place. Imagine, alternatively, a very heavy object, like maybe you have a safe or something like that. It weighs a few 100 pounds and it's on a wood floor, and you try to push it, and you push and it doesn't move, or you lean against it, which is a type of push, and it doesn't move, and you have to push really hard before it starts moving. Or your car, if it stalls out and you start trying to push it and you can't get it to move even though it's on level ground. There's some friction present, and that amount of friction increases until a maximum value. And once you exceed that maximum value, it slides. Now with your car, of course, you can put the thing in neutral and let it roll. But if it's not in neutral and the wheels are like locked or you have the brake on, then you have to push very, very hard before it will start to slide across the ground. So those are basically some simple examples of Newton's first law. Now this was a very topical video. There will be some more that I add to this in future videos, but because this is the introduction to Newton's first law, I didn't want to use too many new forces that we haven't encountered yet to work through it. We'll even have another section on statics after we know a little more about forces. So until then, I hope that you've learned a little bit from this video, and thanks for watching.